Right, so welcome everyone to this new video where we discuss mathematics and physics on the board. In this video, we are going to discuss a very important criterion, which is called the Cauchy-Riemann criterion, and which has to do with basically the starting point of complex analysis. So essentially, how do we talk about analysis of functions and so on when we are in the complex plane? Right, okay, so let's try to understand what kind of problem we are looking at when we want to talk about this starting point of complex analysis. So the thing has to do with, imagine you have a function, and this function actually goes from R2 onto the complex numbers. And so it takes in argument two numbers, two real numbers, and then it's going to return a complex number. And this complex number, because it's a complex number, is going to have a real part and an imaginary part. And so here you're going to have a function, so that's a real function u of x and y, and then plus I, where I is the imaginary number, and then times v of xy, which is also a real function. Okay, now the question we want to ask is that if we have this particular map like this, is it possible to have a function f, which is actually a function that maps essentially a complex number onto another complex number, such that basically to some complex number z, that is x plus iy, we actually get some f of z. And the thing is that we want as well that phi of xy is going to be equal to f of z. So that's kind of the idea. And so working on basically this expression and this particular kind of target, so things we want to ask, then we are going to derive a general criterion for basically this such a function to exist. Okay, so what we are going to show here is that essentially if we assume this particular function to exist, then we are going to get this particular a particular set of criteria. Okay, so we are going to start, maybe I can start here, I'm not sure how long it's going to take. So the first thing we are going to say is if this is true, then this is going to actually constrain what we can observe for the partial derivatives. And so, for example, here, if I write d phi dx, then by the chain rule, this is going to be equal to, I think that's one way it can be written, df dz, and then I've got partial derivative of z with respect to x. And z is equal to x plus iy. So in fact, I've got that d phi dx turns out to be df over dz. Now I can do the same for d phi over dy. So I'm going to do it here. So d phi dy is equal to df over dz. Again, that's if this equation is satisfied, then this is going to follow, and then I've got dz and then dy, and so that's equal to I df dz. Now the reason why this is fascinating is because we've just seen in this equation, okay, we've just seen that df over dz is equal to d phi dx, okay? So what that means is that essentially we are going to have that this is equal to I times d phi dx, okay? So if this is true, then it follows that d phi over dy is equal to I d phi over dx. Now, what we are going to do is evaluate what this is. So because I've got phi of xy is equal to that, I've got phi of xy is equal to uxy plus I vxy, then it follows that d phi dx is equal to du dx plus I dv dx. Okay, so far so good. And then I can do the same for d phi dy. So d phi dy is equal to, and so that's du dy plus I dv dy. Okay, so essentially, obviously, I've got a real and an imaginary part to these partial derivatives, and so when I rewrite this equation, so I'm subbing this here, subbing this here and that there, I'm actually going to get that du dy plus I dv dy is equal to, and I need to be careful because I need to multiply by I that part. So it's equal to I du dx and then minus dv dx. Okay? Now the thing is that the final bit has to do with the fact that if two complex numbers, so if, and in fact, I would say, sorry, I would say something else. I would say that z is equal to x plus iy, and if I've got another w, which is equal to, for example, x prime plus iy prime, we have that z is equal to w if and only if you've got that x is equal to x prime and y is equal to y prime. So essentially you need to equate, the real parts need to be equal and the imaginary parts need to be equal as well. Okay, and that's because you can't convert an imaginary number into a real number, that you can't convert it by linear combinations, and so you need, exactly like in a normal linear vector space, you need to ensure that each component is independently equal. And so here we need to do the same, and we reach the conclusion that basically if this is true, then we must have this set of conditions that follows. So the equality of du dy has to be equal to minus dv dx, and so that's the equality of the real part of these equations, and then we've got the equality of the imaginary part, that dv dy is equal to du dx. Okay, and so these equations are called the Cauchy-Riemann criterion. Okay, so there's a Cauchy-Riemann criterion, and that's in that particular case, that's a necessary condition for this to be true. Okay, so it's not like we prove the entirety of it, because we need to prove that if that, then there is necessarily something like this. This is something that we are going to see by from another angle, basically related to integration. But at least here, that's the idea. So if you don't know how to retrieve these Cauchy-Riemann criteria, just remember that the idea is essentially to have, you start with a function again that goes from R2 onto the complex numbers, and then you want to check whether or not that fits with a function that goes from the complex numbers onto the complex numbers. Okay, so that's it. I hope you found it interesting. If you've got any questions or comments, please let me know in the comment section, and otherwise see you in the next video.